Hello wonderful person, this is Anton, and today we're going to discuss a kind of a landmark moment in astronomical history. Because for the first time ever, astronomers have been able to directly characterize the actual surface of a rocky exoplanet. Something that until recently has never been done before. And while we've spent many years finding various exoplanets and even studying their atmospheres, in this case, actually seeing the surface or the ground of a planet, and a planet that's approximately 48 light years away from us, is a major leap forward. And so in this video, let's discuss exactly what scientists discovered and how all of this was achieved. But first, let's discuss the star system and the planet, starting with the simulation right here created by NASA. This is a system referred to as LHS 3844, a typical M-type star or a red dwarf that very often contains some kind of a terrestrial planet in their orbit. And while this one is no different, and basically contains one planet, or technically one known confirmed planet, Planet B. And extremely recently, both the star and the planet received an official formal name. Here the star is known as Batsu, and the planet is now known as Kua Kua. These names are usually chosen from the list of candidates, and are basically then voted on by a much larger community. And while in terms of overall properties, the star itself is very common. It's approximately 15% the solar mass, 19% the radius of the Sun, and is your typical M-type star. Nothing unusual here. But as you can see from the simulation, the planet is relatively close to the star, and so it's very likely very hot. Which made this a perfect system for astronomers because, first of all, because the star is so small and relatively cool, astronomers have much easier time studying the planets around it. This is actually referred to as M-dwarf opportunity, and is really because the star doesn't produce as much light, so the planets are much easier to see. And the planet is known as the ultra-short period planet because it orbits every 11 hours. Or basically one single year is just 11 hours long. So yeah, 1 year here is half as short as a single day on Earth. But because it's so close to the star, it's extremely likely to be tidally locked. And so only one side always faces the star, with the other side being in the perpetual darkness. And that means that the day side here will probably get super hot, with the initial calculations suggesting that the temperatures could reach up to about 1000 Kelvin or 730 Celsius, 1300 Fahrenheit. So essentially this would be an extreme type of a planet. Which means that studying its atmosphere would be super exciting. And the question is, how exactly was this done? Well, to understand this, we first have to discuss how we normally find planets and how scientists normally study their atmospheres. And normally astronomers use two primary techniques. The first is known as transit photometry. This is actually how TESS mission discovered Kua Kua, or the planet, back in 2018. And so in this case, when the planet passes in front of a star, it blocks a tiny amount of starlight that produces a kind of a dip. And by measuring this dip in brightness, we can then calculate the planetary radius, which in this case was about 1.3 times the size of Earth. And by using the second method known as the Doppler spectroscopy, researchers can then observe a tiny gravitational tug on the star that's produced by the planet orbiting around it. And because of this wobble, which is usually visible in redshifts and blue shifts, researchers can find its mass, which in this case was 2.3 Earth masses. And when combining both, we get density. And here this was 6 grams per centimeter cube, which is just a little bit denser than Earth, essentially confirming that this is a terrestrial planet, but in this case obviously much closer to the star and thus much hotter. And so until now, this is basically what scientists used to characterize most of the planets discovered so far. In this case, we're talking about thousands of different planets. But we could never really study the surface, and that's because it's just very challenging and involves unusual tricks, which is in essence what this new study is all about. And so basically, until now, scientists had no idea if this planet is completely barren, or if it potentially contains a very thick atmosphere like Venus, potentially making the planet even hotter. And while according to some of the previous data from the Spitzer Space Telescope, the initial discovery suggested that it possibly has no atmosphere, because when the planet passed in front of the star, the additional spectral analysis did not reveal anything specific. And in this case, a lot of the atmospheric particles can be seen at the moment the planet starts to produce the shadow, because we expect the atmosphere to obscure the star first. And so in this case, by analyzing the spectra, it becomes possible to discover what sort of molecules might be inside. but more recently, additional observations from the James Webb definitively confirmed that it seems to have no atmosphere. This was actually achieved by conducting what's known as secondary eclipse spectroscopy, when scientists actually watch the system as the planet moves behind the star. In a nutshell, it kind of looks like this and involves very basic math. So basically star plus planet minus star equals planet. And so by watching the system as the planet moves behind the star, and by comparing the light of the star alone when the planet is hidden to the light of the star and the planet together, it becomes possible to isolate thermal radiation coming directly from the planetary surface. And this essentially allows scientists to definitively see reflections from the surface of the planet itself, with the first confirmation here being that it seems to be entirely featureless and basically contain no atmosphere. And if there was a thick atmosphere, the gases would actually absorb very specific wavelengths, creating dips in the spectrum. For example, a CO2 atmosphere like on Venus would create very specific absorption spectra, which were not visible in this case, with the spectrum here being entirely flat. And something very similar has been recently done for the TRAPPIST-1 system, with at least one object also confirmed to contain no atmosphere. But that was just the first discovery, because in this case the observations were so accurate that researchers could then do something else. These James Webb Space Telescope observations could now be compared to various rock models, or various predicted models based on various observations and certain simulations where planetary composition and planetary surface is already known. In other words, they could then compare this and figure out what it seems to contain on the surface. For example, is this a volcanic world? Is this a planet made entirely out of granite? Or does this planet contain something else on its surface? And the first discovery here is that it is not made out of granite, which kind of, I guess, makes sense. On Earth, granite requires plate tectonics and a lot of liquid water, neither one of which potentially exists on this world. So no plate tectonics, no water, means no granite. And instead this spectrum has a best match for a dark, low silica rocks like basalt, very similar to the volcanic rocks found in Hawaii or Iceland, and possibly olivine-rich materials that very likely have volcanic origins. And so these are so-called mafic or ultramafic rocks that normally come from the planet's interior or from the mantle, with the study concluding that based on these observations, right now the surface is extremely likely covered in regolith, or this fine powdery material created by millions of years of space weathering that to some extent resembles what we see on the Moon, or to be more exact, what we see on Mercury. And that's because without an atmosphere to protect it, this planet is constantly bombarded by micrometeorites and solar wind, which slowly but continuously pulverize these surface rocks and turn them into dust. So just like what was discovered on the Moon when the Apollo missions finally landed there. And that's of course something we expect on the surface of Mercury as well. And because no additional emissions of sulfur dioxide or carbon dioxide have been found in these observations, it means that this planet is unlikely to have active volcanism, because even tiny amounts of these gases would have been detected by James Webb's MIRI instrument. And so in this case, researchers can say with very high confidence that Koa Koa does not have an atmosphere, lacks active volcanism, at least on the day side of the planet, and seems to contain a lot of scorched regolith resembling Mercury. Although exactly what happens on the night side is of course unknown. In this case, seeing the night side would be very challenging. And once again, the day side and the night side are definitely very different because this is a tidally locked planet. And so in some sense, this is actually what was kind of discovered around TRAPPIST-1b as well, the closest planet in the TRAPPIST-1 system. Here we have planets whose atmospheres have been stripped away, and that potentially never had water or any volatile materials, and seem to resemble these scorched Mercury-like worlds, except that larger in size and in mass compared to our own planet. But it's really not the planet in this case that's exciting, it's the method and the discovery. Because this marks a fundamental shift in how we study exoplanets. For decades, exoplanet science was all about detection, or basically just proving the existence of these planets, and occasional analysis or detection of atmospheres, mostly focusing on detections of gas, and usually focusing on gas giants. And that's because gas giants in general are just much easier to see, and their atmospheres are much thicker and easier to study. But we have now officially entered the era of exogeology. We're no longer just saying there is a planet here, We can now even say that the planet is made out of basalt covered in space-weathered regolith and seems to resemble Mercury based on the spectral observations. And so if this is done for other planets, it will actually allow astronomers to physically compare geological histories of other star systems to our own, basically confirming the processes that form rocks and maybe discovering processes we never knew existed. Although in this case, the first important confirmation would actually be really simple. Does the cooling of lava produce basalt rocks everywhere in the galaxy, or is this just something unique to planet Earth, and maybe lava on other planets produces something entirely different? And so here, LHS 3844b, officially known as Kua Kua, might not be a place where we're going to be discovering extraterrestrial life, but it's now become a vital laboratory for studying extraterrestrial rocks and for understanding exoplanetary geology. And it also shows us what happens to a planet that's too close to the star and lacks the protection of an atmosphere. And so as additional observations are conducted, and as scientists discover more of these observations from other exoplanets, hopefully in the next few years we're going to move from studying just one bare rock to understanding the full diversity of planetary surfaces across various star systems. So once again, this study seems to be the official birth of exogeology, which means that we'll come back and discuss additional discoveries in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying a Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.